All right, now that we've talked about derivatives, we'll go ahead and begin our discussion of computing areas bounded by curves presented in polar form. Okay, so let's say we have this polar curve described by this equation r equals f of theta, and let's consider this function f over some interval. Let's say theta equals alpha is the lower bound up to theta equals beta for the upper bound, and we want to compute the area of this region bounded by the blue polar curve and these two segments, right, where theta is alpha and theta is beta. All right, now to do that, okay, it helps to think about a windshield wiper, okay, sweeping through this region as we rotate from alpha to beta. Okay, now one complication is that the length of our wiper blade changes as we rotate, right? The length of the wiper blade is described by f of theta. Okay, but nonetheless, we can compute this area using many of the same ideas that we see in Calc 2 with Riemann sums. Okay, so just think about taking little infinitesimal rotations and finding the area of each one of these little wedges, and then what we're going to do is just sum up those areas as theta ranges from alpha to beta, and that's going to give us the total area. Okay, so if I zoom in on just one of those wedges, that's over here, okay, I'm going to call that little rotation angle d theta. This is just a little infinitesimal rotation. My radial distance is r, okay, and you want to recall this fact from geometry that says that if you have a circular wedge, okay, where the circle has radius r and the central angle is alpha, where here it's assumed that alpha is measured in radians, the area of that wedge is 1/2 r squared alpha. So in other words, it's 1/2 times the square of the radius times the central angle. Okay, now our curve here very well may not be the arc of a circle, but if d theta is sufficiently small, okay, this rotation here will be at least approximately circular. And in the limit, okay, this will become more and more circular as you let d theta become infinitely small. Okay, so applying this result then, the area of this nearly circular wedge is 1/2 times the square of the radius times the central angle d theta. Okay, so now we go ahead and just sum up all these areas. I'm just going to copy this graph on the left down below. So to compute this full area bounded by our blue polar curve and these two line segments from alpha to beta, we're going to sum these up with an integral, right? We're going to integrate this expression for the area of the wedge, 1/2 r squared d theta, as we let the rotation angle theta vary from alpha to beta. All right, and then finally noting that r, right, that's described by f of theta for points along this curve, that tells us that this integral then is also equal to 1/2 f of theta quantity squared d theta. All right, great. Well, that's going to do it. In the next few videos, we'll see all of this in action. See you there.